All right, so this is part 3 of chapter 7, flow past immersed bodies or external flows. The slides have been prepared using your textbook, Fluid Mechanics by Frank White. So in the previous lectures, we talked about boundary layers for laminar flow, and we talked about this equation CD, the drag coefficient for laminar flow. So this equation is obtained from the solution of the boundary layers from Blasius solution for CD. And CD is the ratio of the drag force divided by 1/2 rho u square and times the area of the plate. So for laminar flows, similar to the flow inside the pipe, internal flows, this equation CD is valid for both smooth or rough plates. Because the flow is laminar, the roughness actually does not affect the friction, does not affect the drag, because the laminar layer of the flow covers up the friction, covers up the roughness. In the case of a turbulent flow, roughness has an effect. So for turbulent flow, in the previous lecture, we talked about this equation, turbulent but smooth. So if the plate is smooth, or if it can be assumed smooth enough, then CD is obtained, the drag coefficient is obtained from this equation. And usually we consider the transition between laminar to turbulent as Reynolds equal to 5 times 10 to the power of 5. So if you look at this diagram here, this is similar to Moody diagram in pipe flow. We do have CD here on the y-axis, and on the x-axis this is Reynolds number, which is unfortunately covered up, but this is Reynolds number 10 to the 6, 10 to the 5, 10 to the 6, and 10 to the 7, 10 to the 8, 10 to the 9. It's a log diagram on x-axis because it increases every one order of magnitude, but on the y-axis it's a normal scaling. Okay, so if you look at this diagram, which is again Moody diagram of, it is similar to Moody diagram in internal flow. You see this curve here. This is for laminar flow, CD for laminar flow. This is equation, the first one, 727. Then for the turbulent flow, a smooth tube or a smooth plate, this is the curve, which has no effect of roughness in it. It's just this is just a function of the Reynolds number. In between, we do have a transition region. Usually transition region is an unknown region because the flow is highly unstable, and for design purposes we are either in the laminar flow region or turbulent flow region. So that said, for transition region, these equations have been proposed in order to find the drag force in case we are actually in the transition region. So if we take the transition Reynolds number as 5 times 10 to the 5, then this equation 749a of the book is used to find CD, which is a function of Reynolds number only. And if transition is taken a little bit larger, 3 times 10 to the 6, two limits for instance, then CD is obtained using the other equation here, 749b. These two equations are shown here on the diagram for the transition region, CD in the transition region. So then there's another case, turbulent flow, which is not smooth, rough turbulent flow. So as you see on this diagrams, so this is the curve. This is the curve for the smooth turbulent, and then it is connected, and it is actually there's some deviations for different values of roughness. For different values of roughness, it branches out. It has multiple branches, and each branch corresponds to one roughness. For instance, if the roughness ratio is 1000, which is very large compared to the roughness ratios in the tube. So let's see what's going on. Here the roughness ratio is defined as L over L, the length of the flat plate, divided by the roughness. In internal flow, roughness was epsilon divided by D, the diameter. So the roughness ratio in the internal flow is defined differently. So for each values of this roughness ratio, therefore we can use the corresponding branch in order to find CD. And you see that, again, similar to internal flow, for very rough or fully rough plates, the CD becomes independent of the Reynolds number. And the line for each of these cases depends on the Reynolds number as well. So we do have equations for the turbulent fully rough region here, for CF, the skin friction coefficient, and CD, the drag coefficient. So for drag coefficients, we do see we can use the diagram directly, or we can use this equation. So both return the same result. So CD equal to 1.89 plus 1.62 log of L over E, the roughness ratio, to the power of minus 2.5. So in between, from smooth to fully rough, you see the curves here, but we don't have the equation separately in this part, because then we would need to have many equations. So in such cases where it is not fully rough, then the curve can be directly used. All right, so this slide is a summary of what we have had for laminar, turbulent, smooth, and rough plates. This is an important slide. Let's do an example. So let's do example 7.4. A hydrofoil 1.2 feet long and 6 feet wide is placed in a seawater flow of given velocity with given density and given kinematic viscosity. So properties of water, seawater. So we want to estimate the boundary layer thickness at the end of the plate. Okay, so let's do part A first. So in order to estimate the boundary layer thickness, we need to calculate Reynolds number to see whether it's laminar or turbulent. So based on the given values, Reynolds number is larger than 10 to the 6. It's definitely turbulent. So we go ahead and use the correlation or equation for delta over X for turbulent flows. So here X is equal to L, the full length of the plate. So therefore we get delta, the thickness of the boundary layer at the trailing edge. Okay, so here also part B. So estimate the friction drag for several cases, because the plate that we are considering can be considered as fully smooth, so can be considered as smooth, fully rough, or in between. So several scenarios depending on the properties of the surface. So for B, consider turbulent smooth wall. So it's turbulent, we found the Reynolds number. So a smooth wall flow from the leading edge. So if the flow is considered, if the plate is considered smooth, then we do have the equation for a smooth turbulent flow. It's straightforward based on this equation. So we plug in our Reynolds number and find the drag coefficient. And then in order to find the drag on both sides of this plate, because it's in this case we do have a hydrofoil, so water flows above and below of this hydrofoil. So the total drag force is 2 times CD, the drag coefficient, times the velocity term, velocity head, if you call it velocity head, and then the area of the plate. So we found it becomes 80 pound force. All right, so this was based on the assumption that the plate is smooth. C, laminar turbulent flow, so like transition with transition Reynolds number of 5 times 10 to the 5. So in the previous slide, we had two equations for the transition flow, two limits. And our Reynolds number is sort of between that as well. So if, for instance, we are uncertain about whether it is fully rough or whether it is smooth, so that might be, we might want to check that as well to see the range of the numbers at least. So if we want to use that equation, so let's see what will happen. And then finally part D, we want to consider it as a rough wall with a given roughness. So first we will do part C, transition with a given Reynolds number. So it is just the equations are just a function of Reynolds number. There is no roughness in part C. So for part C, with critical Reynolds number 5 times 10 to the 5, we use the first of those two equations, 749A, and we calculate CD. We plug in our Reynolds number, which we have calculated for this problem. So we found CD, which is very close to the CD in section A, in section B, and we find the drag force 72 pound force compared to 80. So it's very close. Finally, in part D, if we consider the plate to be rough, L over D is 3000. So for that given Reynolds number, if we look at the curve, we see that that's actually the curve has flattened. So it's on the plateau or on the leveled part of the curve. So this considers to a condition of fully rough regime for this roughness ratio, and for that given Reynolds number, we see that the curve actually is flat. We could go ahead and either read CD from the curve or use the equation for fully rough, equation 748b. We calculate CD, and you see that it's now larger than the previous cases. It's twice as large as the previous two cases. So we calculate D, the drag force, and it's 184 pound force, which is larger or double the drag force in the previous cases. So you see that the roughness can increase the drag force. So this was the drag force only as a result of friction, and we assume that so at the end of the plate there will be no, for instance, additional turbulence, and there will be no separation of the boundary layer from the plate. If there is separation of the boundary layer, then an area of reduced pressure may also develop there, and we may have actually additional drag because of pressure change. But what we have talked so far for the flat plate, the the drag force that we have obtained is only because of the friction. So it's based on the assumption that the boundary layer does not separate. So it's just a continuous attached boundary layer. All right, so that was for a flat plate. For a flat plate, we were fortunate enough to actually perform analytical analysis. And for the case of laminar flow, we did some theoretical work, and also mathematically we're able to simplify and get even the solution to those equations. For other immersed bodies such as spheres and cylinders, it's more complicated. It's not as easy as we observe for a flat plate in the laminar case. Therefore, experimental works are commonly used. So here we are going to look at some of these experimental works for drag force on immersed bodies with other like shapes. For instance, spherical, cylindrical, cubic, wedge shape, any other type of geometries can be encountered in real applications. So here we have defined it before. The drag coefficient CD defined for a flat plate is the same as defined for any other body. So drag coefficients are defined using a characteristic area. So in the case of a plate, the characteristic area was simply the area of the plate. But in the case of different geometries, the characteristic area may be different. So CD in general is drag force divided by the velocity term times the characteristic area. The factor 1/2 is like, something which comes from like Bernoulli's equation. So we keep this 1/2. It doesn't have a very important physical implication, but it's just traditional, approach. So the area A, which is used in the definition of the drag coefficient, can be, can be of different type. So one, for instance, the frontal area can be frontal area, planform area, and wetted area. So in different cases, we may use different values for this area. So for the frontal area, the body as seen from the stream is suitable for thick, stubby bodies, such as spheres, cylinders, cars, trucks, missiles, projectiles, and so on. So for instance, you have a car moving on the road. So you want to find the drag force, right? So CD is expressed and given in tables in terms of the frontal area. The frontal area is the area which is in the direction of the stream. So that would be the area in the direction of the stream. Then another area would be the planform area, the body area as seen from above. So in some cases, such as the plate, flat plate. So in the case of a flat plate, we didn't actually use the area as seen from the front. We used the area as seen from the top. So it's good for wide flat bodies such as wings and hydrofoils. So for instance, if you consider wings, aircraft wings or hydrofoils, it's more meaningful to consider and express these drag forces in terms of the planform area. And then we do have the wetted area, which is customary for surfaces such as ships and barges, where just a part of the object is exposed, for instance, to the flow stream. So when we consider the drag forces, we need to be careful what kind of area is supposed to be used to calculate the drag force, because From, for instance, tables, you may read CD drag coefficient, and then in order to find the drag force, you need to multiply it by these other parameters, including the area. And that area, it has to be clear and clarified that what area you are going to use to find the drag force. Here we are going to introduce a new concept, the concept of pressure drag. So whatever we had so far for the flow over a flat plate, it was the drag that we actually talked about was because of the friction, because of the viscous flow, because of the viscosity of the flow next to the adjacent to the flat plate. So that was friction drag, meaning that the drag force, which has been created as a result of the shear forces on the surface of the plate. So therefore here the friction drag is created due to fluid viscosity and fluid friction with the solid boundaries. There is another concept or another variable to take into account, and that's the pressure drag. So pressure drag is created in some cases, such as flow over a sphere or a cylinder, where the boundary layer cannot stick to the surface or to the boundaries all the time. So first, let's consider this hypothetical condition. So this is like based on theory if there is no means of separation, or in other words, if the Reynolds number is very small, or if we consider a potential flow. In this case, you see that the streamlines will follow the boundaries of the object very nicely. So you see that on the surface, you can imagine of a friction created if, for instance, we consider viscous flow at very low Reynolds number, where the streamlines and flow field remain symmetrical. So if this is the case, if this happens in reality, therefore the drag force would be only because of friction. So because you see no separation of the boundary layer from the boundaries. However, in reality, so the second one is reality. In reality, the boundary layer separates from the boundary of the object at some point, at an angle. If this is the front, if this is the front point, then the boundary, and if we consider, if we measure an angle theta with respect to this point, then at some point, at some angle, the boundary layer cannot follow. And the reason is that because the flow must turn, right? Because the shape, the geometry is like round, but the flow cannot actually follow the boundary exactly. So at some point, it will separate, and it will go straight rather than continue to go all the way down to 180 degrees and then continue, straight. It will separate from one point. So it's natural. It is something that if you look at it, you could actually intuitively tell that. So what's the consequence of this boundary layer separation? The consequence of the boundary layer separation is that as a result, the pressure drops at the back of the object. So downstream, at this point where you see these circulations, which is called the wake, at this point the pressure drops, low pressure region. While in front of the object right here, the pressure is the maximum. So high pressure in the front, low pressure at the back, it will create a large delta P. So it's not because of friction, but because of this delta P, a force will be applied on this object. Therefore, the total drag force which applies on this object, if I show it in this direction, for instance, which has to be counterbalanced in the opposite direction. So part of it is because of the friction, because we do still have friction in the areas where the boundary layer is attached to the body. This is friction drag, and then the rest of it is the pressure drag. So as a result, we can also define our CD, the drag coefficient, as CD because of the pressure forces, P multiplied by the frontal area, and then CD because of the friction forces. In case 1 here, when the Reynolds number is low, for instance, all of the drag force is because of the friction. In case B, the drag force is comprised of 2 forces, friction and pressure drop. And pressure drop is sometimes, dominant. Okay. So now let's look at the relative contribution of friction and pressure drag, which depends on body's shape, that we will talk about in the following slide. Okay, so here in A, so this is the drag of a streamlined two-dimensional cylinder. So consider this cylinder here. This is not a circular cylinder. This is like an airfoil or hydrofoil. It has a width B, a thickness T, and a chord C. The 3 dimensions in A, and the Reynolds number is 10 to the 6. So like it's turbulent flow. Well, it's not turbulent flow. It's, well, this is for like it's not for the case of a flat plate. So this is for a given Reynolds number. So effect of thickness, part A, effect of thickness ratio on percentage of friction drag. So in x-axis we do have T over C, the thickness over chord. So when it's 0, it means that it's a flat plate. So it's a flat plate at T over C equal to 0. And T over C goes all the way to 1. And that's where you do have a round or a circular cylinder, T equal to C. Or something like that. It depends on, yeah, T equal to C is sort of close to a circular cylinder. So now let's see the contribution of friction and pressure drags. So you see that here when T over C is equal to 0, you have a flat plate. 100% of the drag is because of friction drag percentage. As T over C increases, the effect of the pressure drag kicks in. So for instance, if T over C is 1/2, so this is the data scattered based on experimental data. So if T over C is 1/2, something close to what you see visually in this picture, T is almost half of C. Then 50%, then you see that about how much? About like 25% of the drag is because of friction and 75% is because of pressure. So the pressure drag, the contribution of the pressure drag increases as the object becomes more like blunt. As it becomes more flat, the contribution of the friction drag increases, and as it becomes more like blunt, then the contribution of pressure drag increases, because with a like round body, then boundary layer separation occurs, and pressure, the difference between the front and back of the object becomes substantial, creating a large pressure drag. And in part B here, we see the total drag coefficient CD versus thickness when based on 2 different areas. So before we said that CD can be defined based on frontal area. So for this geometry that you see here, the frontal area is T multiplied by the width B. TB is the frontal area. not the area of the curved, not the curved area, just the straight area, the frontal area. And if CD is calculated, if the drag force is to be calculated based on planform area, the planform area would be the area as seen from the top. So it would be B multiplied by, if you look from the top, C times B would be the frontal area. So if we consider, for instance, based on the planform, when we look at it from the top, and when T over C is equal to 0, then we do have a flat plate here. T over C is 0, it's a flat plate. Then for a flat plate, CD, we remember from the previous example, CD was very small, 0.00 something. And it is, for a flat plate, the area is actually the planform area. And as you see, as the thickness ratio increases, the drag force increases because of the effect of the pressure drag. So for a flat plate, there is no pressure drag based on the assumption that the boundary layer will always be attaching to the surface, to the boundaries of the plate. Okay, so we were speaking about boundary layer separation. So here we do have additional information and additional clarification. So let's say this is a flow past a circular cylinder now. We want to compare the laminar flow separation with turbulent flow separation. So in B, we do have a laminar flow. In B, we do have a turbulent flow. So like, all right, so what will happen? What will happen is that a flow approaches the cylinder with a velocity V and with a pressure P infinity. So far from the sphere, the velocity is V and the pressure is it's called like ambient pressure P, which are like constant, for instance, if it's like a uniform flow approach. So what will happen is that on this point, the flow will come to complete stop. This is called a stagnation point. The velocity will be converted to pressure as it approaches to this point. The velocity is like it comes to a complete stop. So the kinetic energy is converted to pressure energy. Then a boundary layer forms. So if you look at here, this picture here, so here the velocity is the flow stops on this point, and then a boundary layer forms on the surface of this sphere. Even in this theoretical assumption, or in the actual case, in the front of the object, the velocity field or the streamlines look kind of similar. You know, if you look at the first half of it, they look similar. The problem or the difference starts, I know, at the back, downstream of the flow. So what you see here is that the flow will accelerate as it moves over the surface of this body. So the flow accelerates and the velocity increases somewhere like on the top of this object at 90 degrees. The velocity becomes like the maximum because it's accelerating. So if we look at this diagram here as well, this shows the pressure coefficient Cp. This is a little bit advanced, so we just want to mention about the separation point. So the details of this second diagram, the Cp, the pressure coefficient, is not really necessary to understand it. So this Cp is pressure at a given point on the surface of this object, minus P infinity, the pressure far field pressure, divided by the velocity potential. So you see that at 90 degrees, for this theoretical limit, which is like either inviscid, this is for based on inviscid theory. The pressure at 90 degrees is the minimum because Cp, the pressure coefficient, is the minimum. So, however, for the actual case, you see that the Cp curves are different. First, we have it for a laminar flow and also for a turbulent flow. And we see that this minimum pressure occurs at different points, for instance. So the shape of these curves are different. So this suggests that the separation of boundary layer from the boundaries of the object actually occur at different angles. This theta angle is measured with respect to this point. For a laminar flow, the separation occurs at an angle usually less than 90 degrees. So, for instance, it occurs here. So, in the first, it occurs, in the front of the object. So, the boundary layer separates kind of early. So, the boundary layer separates early. So, it creates, because the boundary layer separates early, it creates a large area of low pressure here. It creates a large area, a large wake. It's called, we see here, broad wake. So as a result, you can expect that in the case of laminar flow, where separation occurs early, delta P is large, and then when it's multiplied by the area, the pressure drag will be large for a laminar flow. Simply because the boundary layer separates too early. It creates a lot of pressure drop. It creates a large pressure drop at the back, so pressure difference will be large. If in the case of a turbulent flow, because it's turbulent, it does have, well, we can look at it this way, it's turbulent, it does have more kinetic energy, so the boundary layer remains attached to the surface, at a larger angle. In this case, it's like 120 degrees. Because it does have more energy, it can continue for a longer distance along the surface of this circular cylinder. So in this case, the wake will be a narrow wake. So in this narrow wake, therefore delta P, which is created, will be smaller. There will be probably more friction drag in the case of turbulent, but the pressure drag will reduce. So this is very important. This has very important consequences because we see that when we want to, for instance, design something, if this is important to know when the separation point occurs and how the pressure drag and friction drag and total drag changes in order to be able to reduce the drag force. If you look at here in A, so we have two balls, and these are bowling balls. One is laminar, A is laminar, and B is turbulent. So how to make that turbulent? So in both cases, the speed is the same. The entering speed is 25 feet per second. Both of them enter at the same speed. So their Reynolds number would be the same. But how to make one laminar, the other one turbulent? So in case B, sand particles have been attached to the surface of this ball in order to make the flow over this ball turbulent. Roughness creates turbulence, right? So in case A, where it's laminar, so you see this looks like this is the front. This is like where your velocity, if you want to compare it with the previous slide schematic. So this is a stagnation point, and then this is the separation point, occurs at You see it occurs at about 90 degrees or maybe less than 90 degrees. So occurs here. But in this case, in case B, when we have made the surface rough, then the boundary layer separates at a larger angle. So again, this is the stagnation point. And you see that if you measure this angle is now larger than 90 degrees, but this angle here is like less than 90 degrees. So in case A, the laminar flow, visually we see that separation occurs at a smaller theta, a smaller angle, and therefore in case A, we have a broad wake area. You see the wake area is broad. So here, down here, the pressure is low. Here the pressure is high. High pressure, low pressure, there is a large delta P. It wants to stop the ball. In case B, the separation occurs at a longer angle, so this area is smaller. The area of low pressure is smaller, and overall delta P, or the pressure drag, is smaller in case B, which is turbulent. So as a result, we could see that in case B, the ball will attain a larger speed, or a larger it will move faster. Let's put it this. It really depends on the other things as well, whether it's going to accelerate or decelerate, but there will be less drag force in front of the ball in case B, where it's turbulent. Oh, so we do have some more information here. The laminar flow, case A, separates at about 80 degrees. CD drag coefficient is 0.5. While the turbulent flow in case B separates at 120, and this case B, CD is 0.2. And Reynolds numbers are exactly the same because velocities are the same. So CD for case B is 0.2. So of course the forces, the drag force applied on case B is less than, it's 40%. The drag force acting on the ball in case B is 40%. 0.2 divided by 0.5 is 40% of the drag force acting on case A. All right, so let's stop here. This lecture is becoming too long. So in the next lecture, we will continue from this slide, figure 715, where we talk about the importance of body shape in reducing the drag, different kinds of body shapes, and so on.